Welcome, everybody. It's my pleasure to present you our next speaker, Professor Karim Adiprasito, who will talk about some combinatorial commutative algebra. Karim?
Yeah. I actually don't know whether that was the actual title in the program, but I mean, what I want to do is I want to give you a little bit of more properties and useful ways of thinking about these phase rings or Stanley-Riesner rings also sometimes that we encountered in the last section. I'm sorry I cannot be there in person. All right. Okay, so let me start with something that I find very useful, but it's not directly Stanley-Riesner rings. So it's related to it's basically using another model. So what I want to say is the following. It's kind of, you would think it's kind of natural. What happens if I have a subdivision of simplicial complexes? All right, or in other words, I mean, if you want to see it in the other direction, right, it's a simplicial map. So if I have a subdivision of simplicial complexes like that, okay, and I want to in some way encode this as on the level of Stanley-Riesner rings. Okay, so first of all, I mean, what is a subdivision then, and how would I see this on the level of Stanley-Riesner rings? So, but now here's a trigon and here's a fourgon, all right, and I want to say, okay, so I have 1, 2, 3. I have 1, 2, 3, and then I have a new vertex 4 here. I claim that there's a natural map, and at first it's totally not clear where would this come from, right? So there's a natural polyhedral map that sends simplices to simplices in this direction. That's fine, but how does it induce like a map of Stanley-Riesner rings? And that's not so clear. And the idea is the following. Let's jump to another object, and this is kind of useful, and this is to think about fans instead of simplicial complexes. So what is a fan? Well, I could, if I look at this trigon, all right, sitting in my space, right, it's the same trigon, it's just the way, I mean, okay, so there is a function how to do this as a copy, but I mean, the idea was, I mean, it's supposed to be the same trigon, doesn't matter. So what I can do is now I can, over every face, I can draw a simplicial cone, right? So I have this face 2, 3, and it now corresponds to this simplicial cone, right? And then I have, let me do it another. So this is another simplicial cone, and this here is a third simplicial cone, right? So there are now 3 cones here. And if you want, I mean, okay, so you might think, why I do this? Well, this is actually really, if you think about it, where Stanley-Riesner or phase rings come from. It comes from toric varieties and toric geometry, and they are naturally associated to fans, right? And then it's kind of it's more natural to think about a subdivision, perhaps. The subdivision now is a subdivision of fans, right? So you want to say that every fan of the new, right? You have the same underlying space, but every fan of the new object is contained in the fan of the old every cone of the new object is contained in the cone of the old object. So I mean, I obtain the following, right? I don't draw the quadrangle again, I just draw it like this immediately. Right? So I have this cone is now subdivided into these 2, and the other ones are unchanged. All right. So now I claim that there's naturally a map of Stanley-Riesner rings between the 2. Okay, so why is this? Well, it turns out that it's useful to think about another object. So if I have a fan, which I can now, right? So I did the following step, right? I started with delta simplicial complex. And what I associated to it was a fan. We call it f of delta, a fan. No? And now the next step, right, associated to this fan I want to find an algebraic object, and this is the ring of cone-wise polynomial functions. So P of F delta, it's a ring of cone-wise polynomials. Polynomial functions. Okay, so let me put this a little bit. Okay, so the ring of cone-wise polynomial functions. Okay, technology. Up here, I have the Stanley-Riesner ring, right, or the face ring. So I have my ring. Let me call it small. Let me denote the ground field by a little k, and then I have k of delta. All right. Ignore for. I mean, if you prefer, think of characteristic 0. If you have trouble of thinking about fans and other characteristics, doesn't matter. Okay. So there's a ring of cone-wise polynomial functions, and there's the ring or the face ring here. So how are they related? Well, let's just observe that. Okay, so this ring here, this ring of cone-wise polynomials, it's also graded, right? P of delta is graded. How? Well, I mean, there are those functions that are linear on every of these of the cones, right? I mean, I could draw the level sets like this, like this, like this, like this. And then there are those functions that are quadratic on every cone and that are cubic on every cone, and so on and so forth. Right? So this is a graded object as well. So now we can also think about the degree 1 objects, so what were the generators of this, right? And it turns out that the generators in degree 1 are, okay, so these are functions associated to rays. So let's say I have a ray here, right? So this is a ray rho. So then, and generate, so it's generated by rho, chi of rho. What do I mean by chi of rho? It's a characteristic function of a ray. So this function is linear and non-trivial. Let me just not normalize it for the moment. Then linear and non-trivial on rho and 0 on all other rays. On all other rays. Okay? And then what I do is I just continue this linearly. Okay? So I mean, I have it given on the rays. So here is 0, here it's 0, here it's 0. And on this ray, it's somehow this, on this additional ray here, ooh, it's chosen red. On this ray, it is non-trivial. So it starts at 0 here, it's linear. But then at some point here, it attains a value 1, right? Somewhere. Okay, it's linear, it's not trivial. So on this ray, it must attain some value. That's just somehow, somewhere it attains 1. Could be on the negative side, but let's ignore that. Okay. Okay, and it turns out these generate. Oh, okay. And now what I could do, I mean, I mean, K of delta is also generated, right? By, well, I mean, what is it generated by? It's generated by some variables associated to vertices. But the vertices in this fan complex, right? The vertices over here, right? This one, oh sorry, the vertices in the original simplicial complex, they are exactly the one-dimensional rays, right? So the one-dimensional cones, the rays. So it's also like this. So I could look at the map sending x rho to the variable, or chi rho I could send to the variable x. Okay, and this turns out to induce this isomorphism. Okay. All right. And now you can think about immediately how subdivisions are supposed to be satisfied. So subdivisions. Okay. So subdivisions Well, subdivisions, how do I, okay, so I claimed that there's a map, all right, again, from here to here. All right, I have an additional vertex now. And how do I see this? Well, I could do the following. All right, see, now I can do magic. Like this. Like this. All right, I have the cone complex constructed, or the fan, or constructed over the simplicial complexes. And now, okay, so instead of constructing the map up here on the level of Stanley-Riesner rings, I can immediately construct it down here. All right, it's trivial. So I have the space of cone-wise polynomials here on this fan, delta. All right, so let me call this delta, and this is delta prime. And I have the space of cone-wise polynomials here. And I claim that there's an obvious map, all right? And in fact, there's an obvious embedding here. And why is that? Well, every cone-wise polynomial here, all right, on the former, is still cone-wise polynomial on the latter, all right? Because it's a finer fan. I cannot do anything about that. All right. Let me note that this fits with Vasiliki said at the end of the last section when we talked about these the modeling out this linear system of parameters, right? The linear reduction. So remember, what we did there was I took this Stanley-Riesner ring, and then I modeled out some linear forms, theta 1 to theta d. All right, so these were just some linear forms. All right, and okay, so how does this look in the picture of PF delta? Well, let me reinterpret this information here up here a little. Okay, so let me remove this. All right, I mean, this is an abstract simplicial complex, and I add a matrix. So this so instead of looking at the linear forms, I write somehow a big matrix here, and I multiply it with the vector of indeterminates. Right, that's just another way of writing these linear forms. Okay. Okay, and now I have a matrix here, and this matrix has entries over K. All right, so this is matrix over a ground field. Okay, so this associates some vectors in my space, right? To every single vertex here, or somehow to every vertex, we associate a vector in K to the D. Okay, where D is just the number of linear forms that I had. Okay, and what I do is I look at consider the fan complex, or the cone complex, the fan generated by these vectors. What do I mean by that? Well, okay, so I have my origin, and then I have a vector for one vertex, I have a vector for another vertex, I have a vector for another vertex, and I have a vector for another vertex. And now if I have this, let's say 1, 2, 3, 4. Now if I have the simplex 1, 2, then I get in the fan, I get the fan spanned by these two, and sorry, the cone spanned by these two, and then the cone again spanned by 2 and 3, and so on. All right, I get this fan. All right, so I now have, all right, so this leads to P of delta, where F delta is realized in K to the D. All right. And now you remember that I magically kind of associated, right? I magically associated a slide or two ago, this point here where I attained the value 1, that is exactly this coordinate for the vector. Okay, so here in the characteristic function, my function attains 1. All right, that's the normalization point. All right. And now I have a natural map. Now the question is, right, what do I mod out on this side? Well, it turns out that I mod out exactly the ideal generated by the global polynomials. Global polynomials. Okay. So okay, so global non-constant, I should say. So let me be precise. Global let me do it like this. So it's a global linear functions. Okay. And that's it. So this is the isomorphism. And then you can think about, well, how does this help me? We will see later. But one of the key points is, right, now Wasser talked in the last lecture about Cohen-Macaulay complexes or Cohen-Macaulay rings. And one of the key examples is that we take just the boundary of the simplex. So this is this is the boundary of the simplex on vertices 1, 2, and 3. Okay, and it turns out that this here is one of the simplest examples of a Cohen-Macaulay complex. It exactly corresponds to a projective space. Okay, so K of delta, it turns out to be Cohen-Macaulay. All right, and it turns out that one of the crucial operations that preserve this Cohen-Macaulay property are subdivisions. So Cohen-Macaulay is preserved under what is called subdivisions, under subdivisions. All right, so this here is also Cohen-Macaulay. Okay, now this is one of the first useful observations that you can make. So that once you do some elementary manipulations, you preserve the Cohen-Macaulay property. And this, if you think about it, this gives you already a lot of Cohen-Macaulay complexes. And then you get the suspicion that there's perhaps a topological characterization of this Cohen-Macaulay property. And this is exactly what I want to talk about. This is the Reissner property. Okay, so Reissner theorem. So part 2, Reissner theorem. And the partition complex. Okay, so Reissner theorem is a classical theorem in combinatorial commutative algebra. It basically says this Cohen-Macaulay property, right, this algebraic property, we can characterize in a topological fashion. And what I will do is I will try to sketch a proof for you using this tool called the partition complex. Okay, so this is a partition complex. Is something that at some point I came up with. It's a kind of useful way to thinking about these objects. So the idea is the following. We want to analyze our. Let me first state the theorem. Okay, so theorem. Let me. Okay, so let me first give you a definition. Okay, definition: delta is topologically called Macaulay. If delta is of dimension d minus 1, and in every link the homology vanishes below the top dimension. That is, what do I mean by that? Well, okay, so I want to say that if I look at link of sigma in delta, so I have a phase sigma, all right? So sigma, all sigma element in my simplicial complex. This includes the empty phase. Link sigma and delta. I have that I can look at the reduced homology of this object. And what I want to say is that this is 0 unless, okay, so now I have to get the dimension right, unless I is equal to sigma, d minus 1 minus the dimension of sigma. Now I have to be careful. For the empty phase, I want this to be, so this would be minus 1, so I have to plus 1. Okay? So d minus dimension sigma minus 2. Correct? I hope so. I always get the indices wrong. Was there a comment?
By homology, we mean just the visual homology.
I didn't hear it.
By homology, you mean the usual simplicial homology?
Yeah. Usual simplicial. Okay, so usual simplicial homology with k coefficients.
Okay.
With k coefficients. Thank you, Dasha. All right. All right. So I stated topologically called Macaulay, and we have the usual called Macaulay of rings. So they should be in some way connected. And that's exactly the theorem, Reisner theorem. If delta is topologically called Macaulay, and I will specify over a field K, then K of delta is algebraically called Macaulay. And again, this is over K. All right, so specific to the field, not specific to the characteristic at least, and vice versa. Okay. And I will try to sketch you the argument. One lemma I will use, lemma is that let me state it the following way. If delta, or delta is called Macaulay in both senses, in either sense, if and only if cone of delta is called Macaulay. Okay. So in particular, so let me say, all right, so cone, what is a cone of a simplicial complex? All right, that's just if I have a simplicial complex, I can attach another vertex, and this vertex I connect to everything. Okay, that's it. Okay, that's the cone. In particular, the star of a vertex is called Macaulay if and only if the simplicial complex itself, the link is called Macaulay. And now there's the following is the useful object, the useful way of thinking about it. We want to look at the space ring, and now we want to in some way analyze it topologically. So what would be a natural way of analyzing things topologically? Well, I could look at restrictions to stars. So this here, I have the star of a vertex in delta. All right, and that's a natural map. Okay, but somehow that's kind of, I mean, what should I think about, right? I have my simplicial complex sitting in some way in some space, and now what I do is I want to look at the restriction to this star here, all right? Just this star. Oh, that's just, I mean, I just specified that there's a star of this vertex is exactly the star this vertex V. All right, so this is delta. All right, so this is a natural map. And now what I want to do, right? I want to do the most natural topological thing. I want to cover the complex by its stars. All right, the stars are contractible, and that's always a good thing to cover a space by contractible subsets. Okay, and then I have the direct sum over the vertices in delta. So let me move this a little. Okay. All right, but now if you remember a little bit from the nerve complex, from all this, from Rips complex, nerve complex, these kind of things, you don't want to do only this. You really want to go a step further, right? You have a covering, but now you have the intersections of these things that you covered by. So you want to go, and the next step would be I look at the covering by edges. So E in delta, okay, star of E delta, and then right, I continue and I cover, right, here I would look at sigma in delta, and let me do it like this, sigma in delta I, where delta I is those sigma dimension of sigma is equal to I. All right, and that's a complex. All right, this is a rather interesting complex. All right, so it turns out, so if I restrict this complex I call P of, I shouldn't have called it P. I mean, okay, so there are too many P's already, but this is called P of delta, and I will denote it by a little dot. That's supposed to be it's not. Sorry, I mean, this is not the ring of convex polynomials. This is this partition, what I call the partition complex. Of delta. right? It partitions your space, your element in the standard ring by looking at the restrictions to local to vertex stars, and it has nice properties. Right, in degree 0. Maybe. So here this is P of delta, and then I start with a 0. Okay, so this partition complex in degree 0 is just this Čech complex, Okay. In positive degree, topologically called Macaulay implies that it is exact. Okay, so it's not quite an exact complex, but in positive degree it is. All right, so if I restrict to K delta J, where J is larger equal to 1, and I look at delta, right, I look at this complex delta in this degree, then this complex is exact. All right. Okay. And now, okay, so what's the next thing that I want to do? Well, I wanted to relate this, right? I want to at least tell you a little bit about the implication of topological Cohen-Macaulay into algebraic Cohen-Macaulay. Okay. And how do I do this? Well, algebraic Cohen-Macaulay, if you remember, it says that if I take K of delta, and I mod out, right? I take these theta 1 to theta d linear forms, right? So delta of dimension d minus 1, sorry. All right, and I take these delta d linear forms, then these act as regular elements. So this is a regular sequence. All right. So I want to mod out these delta d and these theta I regular sequence. That's what I want. All right. So how do I do this? How do I achieve this? Well, the trick is now, let's look at this partition complex. So we have P of delta, and I want to do some magic with it. But in some way, I also need a complex encoding these theta I. And so what I do is exactly I look at the Koszul complex generated by these theta I. Okay. So what is the Koszul complex? All right. What is it? Well, this is exactly just the product of overall I in 1 to D, where I take K theta I, so the Koszul complex of a single element. So I take the tensor product of the Koszul complex of single elements, and now I have to just explain to you what K of a single theta is. And what is it? Well, this is just a complex given by, I have my ground ring, right? X, right? And I have the multiplication by this little theta. Right? So this is a very short, very short complex. And when I tensor it, I get this nice complex on the exterior algebra. Okay, so these are two complexes, and I want to marry them in some way. I want to combine them. And what I do is I basically just tensor them. Okay, so I basically take the double complex. So I take the double complex consisting of P delta and I combine this with this cos2 complex. Okay, so what does this look like? Well, I mean, in one direction, this is just, I mean, right, this is just the P delta, all right, so it's just I have K delta here, and I go to the star of the vertex, K of the star of the vertex, so on and so forth. And if I go into the other direction, all right, in this direction, I have the cos2 complex. So I have now K, okay, so now I have these D-linear forms, so K delta, and this is the, then I have a choose 2 delta, and I have these multiplications vertically, all right? So this is coming, this is the direction of the cos2, and this is the direction of the partition complex. Okay. So now the idea is the following, that delta being Macaulay, so, okay, sorry, K of delta Macaulay is just saying that if I take cos2 complex, sorry, not the double K, if I take the cos2 complex of this theta, and I tensor this with K of delta, then this is exact, except for the terminal object, for the terminal homology. All right, so in other words, all right, if I'm calling Macaulay, if and only if the homology, if I compute the homology of this chain complex, this vertical slice here alone, then the homology is concentrated just here. All right, so this here again, this here at the top, it goes to 0. All right, it has some kernel, and now I want to know, well, what is the last homology? The last homology group is just K of delta modulo, well, I mean, K delta theta. All right, that's just, I mean, it's just the ring that I want, the reduction by P of K delta by these linear forms. All right, so this will be non-trivial in general, but all the other homologies here and so on and so on vanish. Okay. And now what you want to do is you want to compute the total complex. So the idea, and I will just give you the basic idea, you want to compute the total complex. Okay, what is the total complex? Well, you basically look at diagonals. Okay, so you have this big array, and you group this up with this entry and this entry and this entry and this entry. You take the direct sum. All right, direct sum of this. And then you also have the direct sum over, let's say, these objects. All right, so these kind of encompassed by a rectangle. And again, you have them on a diagonal. All right, and you take the direct sum. And the total complex, somehow this big object before was a double complex. It was graded in 2 directions. And this total complex is just combining the diagonals into one, so that I have again a chain complex. So I have P of delta tensor K. Okay. And now the point is you want to compute this, all right? You want to compute this. This. And now there are two tricks that help. So it's a total complex of a lot of spaces. It sounds kind of scary, right? Except it's kind of, I mean, it's not so scary if you think about it, right? If you think about just the vertical component here, right? If you just think of the pluses on this diagonal, and I just look at the vertical components here, right? Okay, so maybe I don't know what happens on k delta yet, but what I know is that if I look at the stars of vertices and the stars of edges and the stars of higher dimensional faces, then by induction on the dimension and the lemma, I already know that this here is exact except for the last entry. All right, that's now the vertical slices at links or at stars are exact already. Right? Yeah, sorry. Okay. Yeah, I'll come out. I have to just 1 second. Okay? Yeah. Yes. Yeah. Yes. So I have the vertical parts that I already know to be exact, and I also know that in positive degree this complex, right? Some more two information by induction. In the direction of the Kosu complex, I am exact at non-trivial stars. And the second part is in positive degree, I'm also exact. Okay, so I have these two parts. Okay, and it turns out that, okay, so now you have to juggle this around a little bit. You have to think about this a little bit. But this turns out to say that the cohomology of the Kosu complex, so of the total complex. Okay, so let me write it like this: of the total complex is essentially the cohomology of delta, and this is the cohomology of the partition complex reduced. So let me write what p delta theta, which is just p delta modulo this linear system parameters. Okay. And what does this mean? Well, okay, so the cohomology of the total complex means, okay, so the cohomology of the total complex, this means that in particular, because my cohomology vanishes except at the top, vanishes except at the top, this in particular means that if because I'm Cohen-Macaulay, this in particular means that topological Cohen-Macaulay implies the algebraic Cohen-Macaulay. Okay, and this is one direction of this Reisner theorem. The other direction is kind of easier. You just have to remember that localization, how the localization behaves with respect to Cohen-Macaulay properties, and how localization behaves with respect to links. What the connection is there. Let me not go over that because I want to go over a secondary property, and this is partition of unity. The secondary corollary is partition of unity. Okay, so what is partition of unity? Well, I have this map, right? I have K of delta to the direct sum over the vertices of vertices in delta, all right, to K star of delta. All right, and so on and so forth. That was the partition complex. But now I also have the same thing with theta modded out, all right? And that was P tilde of delta. And what does it say here? All right, the cohomology of P tilde delta is exactly the cohomology of this complex delta, and it's exactly the cohomology of the total complex. So a secondary corollary I have is that if I look at K delta modulo theta, and I take the direct sum of vertices in delta 0 here, we put delta 0 here, K star of vertices in delta, then this map here is an injection. In particular, more generally, actually, this complex that I have here, right? Next, I would go to the direct sum over the edges in delta 1. This complex here, well, what is it? Well, I mean, that's just exact, right? So the complex is exact up to the dimension of the homology of delta. This is exact. So P tilde delta is exact up to the homology of delta. Okay. So this in particular means, okay, so that's a kind of, this is a partition of unity. Partition of unity is for me just the injection of K delta modulo theta to the direct sum over the vertices K delta modulo theta. Sorry, modulo theta. Okay. This here is injective in degree less than D. All right. Because degree D exactly corresponds to the homology of delta, which can be non-trivial. Now I promised you that we also talk about manifolds a little. So what happens if delta is a manifold? Instead of Cohen-Macaulay. So what is a manifold? I mean, in particular, a manifold is kind of locally Cohen-Macaulay, right? The neighborhood of every vertex is the disk, and disks are Cohen-Macaulay, right? They're topologically Cohen-Macaulay, and as we saw now, they are also algebraically Cohen-Macaulay. So manifolds are so-called Buchsbaum in particular. And again, this is the algebraic way of saying it, but this is just saying locally Cohen-Macaulay. Okay. And so if I look at this map then, so final theorem is partition of unity for manifolds, or that means for Buchsbaum complexes / manifolds. And now this is somehow the beautiful connection to homology that I want to talk about. And this is, okay, so I have K delta, all right? And I map this to, I want to map this to this star of vertices, small direct sum of a star of vertices, V in delta 0, K star of the vertices over of delta. And I mod out my linear system of parameters, these theta. And I want to, okay, so in general, this will not be, in general, not injective. Not injective. So let me try to understand this in a more fine way. Let me look at the degree I component here and the degree I component here. Okay, so I'm looking just at those homogeneous polynomials of degree I, and I want to understand it then. And it turns out that this is related to the cohomology in degree, well, now you have to be a little bit careful. It's I minus 1 of delta. Okay, so this is a cohomology. This theorem. And now this is not quite the cohomology because we have these Koszul complexes, and then in the Koszul complex we have some exterior powers appearing. We actually get this to some power, and the power is exactly D choose I. And now I'm exact. Okay, so. And this explains more generally what happens in Cohen-Macaulay complexes, because in Cohen-Macaulay complex, this part here vanishes. So I just have the exact, I just have injectivity except for the top degree. Okay, in particular, now this strengthens the partition of unity for Cohen-Macaulay complexes. And again, CM complexes, it's used in different ways in throughout mathematics, so you shouldn't. So it's Cohen-Macaulay. It's Cohen-Macaulay. Cohen-Macaulay. Okay. And that's it. That's a beautiful connection to a homology, and this you get all out of this double complex that we studied now. And I mean, there's another point that you can ask. Well, is this how do I construct this map in a direct fashion? I don't quite have time to cover this, so let me not start it. But there's a beautiful way of understanding this map here in a direct geometric fashion. In particular, if you accept that there is another object. So I introduced this object of phase rings. I introduced these Cohen-Weiss polynomial functions, and these two are related. And then there's this third object of Minkowski weights, and these Minkowski weights allow you to basically understand this map directly. But let me not go into this and leave it here. And if you have questions at the moment, please ask. But that's basically what I wanted to speak.